Welcome to Ask and Learn.
We are given the diagram of a circuit, and we are asked to solve the differential equation associated with this circuit, as well as approximate solutions to this differential equation. In part A, so the circuit we're given has four distinct parts. We have E, which is our battery, which supplies voltage. And we're told that voltage is supplied constantly at 60 volts. C is our capacitor, which we're told has a capacitance of 0.05 henries. And R is a resistor, which we're told has a resistance of 5 ohms. And finally, we have a switch, which determines whether or not the circuit is open or closed. By Kirchhoff's law, we know that the change in voltage, so the voltage drops, summed together equals the voltage coming out of the battery. So we have that the voltage drop across the resistor is Ri, and the voltage drop across the capacitor is Q, where Q is the charge, over C. So Ri plus Q over C is equal to E of T. But by definition, I, the current, is the same as the change in the charge with time, or dq dt. So we can substitute that into our equation to get R of dq dt plus 1 over C times Q equals E of T. And we can simplify this even further by plugging in our values for R, C, and E of T to get 5 dq dt plus 1 over C, 1 over 0.05 This is the same as 1 over 0.05 is 20. Q is equal to 60. So we see we have this ordinary differential equation, which has degree of 1. It's a linear differential equation. In part A, we are asked to draw the slope field of this equation. So we can simplify this first by writing this as 5 dq dt is equal to 60 minus 20q, so that dq dt, which is also q prime, if we think that q prime is the derivative with respect to time, is equal to 60 divided by 5 is 12, minus 20 divided by 5 is 4. So this is 12 minus 4q. We can actually make this even simpler by writing this 4 times 3 minus q. So we now have here our differential equation in a form that's more familiar to us. So if we take C to be some real number, which is dq dt, then we have that the slope to have this value, it must be that C is equal to 4 times 3 minus q. So in particular, we see that Q must be equal to C over 4 minus 3 negative, or 3 minus C over 4. Whereas C is not the capacitance, this is just some real number C. So this Q is actually a function of time. So what we have here is a series of horizontal lines in our graph of Q of t versus t. The points on which all have the same slope. So we see that in particular, if we have C is equal to 0, then Q is equal to 3. So we have 3. All the points on 3 are going to have slope 0. We know that if C is going to be greater than 0, then it follows that Q is equal to 3 minus C over 4 is going to be less than 3. So we see that as we go further and further below 3, our slopes are going to get steeper and steeper. So in particular, at say Q equals 0, or Q equals negative 1, we have C equals 16. Q equals 0, we have C equals 12. So it gets quite steep quite quickly. It's going to be pretty hard to draw actually in this, so I'm going to redraw some of this. I suppose I really don't need to draw the second quadrant either, because we're only concerned about positive t generally. So I'll move the y-axis over as well. This will be 3, this will be 2, this will be 1. And this vertical axis is Q of t. Now, as I discussed, as we get further and further below the line Q of t equals 3, our slopes are going to get steeper and steeper. So if Q is equal to, say, 2, then we have C is equal to 4. So already very steep slopes here. And this is just an approximation of what this should look like. until we're essentially almost vertical as we cross the x-axis. And we see that if c is going to be less than 0, so that we have negative slopes, q is going to be greater than 3. So in particular, if q is equal to 4, then we'll have a slope of negative 4, so already pretty steep. And we see that as we get further and further away from the line qx equals 3, q of t equals 3, that we simply get steeper and steeper until we're nearly vertical. So this is one part of the slope field, probably the most important part to see. And that's our answer to part A. In part B, we are asked to find the limiting value of the charge. So what is the value of Q as t approaches infinity? Well, this does not actually depend on our initial value. So no matter what we pick for y of 0, we see that if we follow these slopes as tangents, you will always end up following the line at q of t equals 3 as an asymptote. So we see that no matter which solution q of t, no matter the initial values, we do see that limit as t approaches infinity on q of t is 3. And there's a more analytical way to see this. So limit as t approaches infinity on q of t, you can see just from the graph this is equal to 3. Alternatively, another way to find this is we're assuming that we reach a steady state which implies that change in the charge of time eventually is going to be 0. So we have the limit of this as t approaches infinity is going to be 0. And therefore we have that this, the limit of this, which is equal to the limit as t approaches positive infinity on 4 times 3 minus q which, using our properties of limits, we can simply write this as 12 minus 4 times the limit as t approaches infinity on q of t. And we can solve this to get that the limit as t approaches infinity on q of t is equal to 3. And this is because, again, we assumed a steady state, which means that as t approaches infinity, the derivative will equal 0, as limit 0. In part C, we were asked to find an approximation so you're asked first if there is an equilibrium solution. Remember that an equilibrium solution is when we have some constant c in the real numbers such that eventually change in our function is equal to this constant. Well, this implies that 4 times 3 minus q is equal to c. Therefore, this implies that q is equal to 3 minus c over 4. This is what we calculated earlier. And we know this is an equilibrium solution if c is equal to 0. So we have an equilibrium solution of q of t equals 3. In part D, you're given an initial charge. We are asked to sketch the solution curve using the direction field. So, back to, we're given that the initial charge q of 0 is equal to 0. And if I graph this in red on our slope field, you see that we have a point at 0, 0. And if I follow the slope field, we quickly increase following these tangents until we start leveling out at around q of t equals 3. And we follow that as an asymptote. Looks a little bit like some kind of exponential growth. In part E, we're given the initial charge is again q of 0 equals 0, and we're asked to use Euler's method with a certain step size to estimate the charge at a certain time. So you're given, once again, that q of 0 equals 0, and you're asked to use a step size h equals 0.1, and to find the charge approximately after half a second. So from what we're given, we know that x naught is equal to 0, and y naught is y of x naught, which is still equal to 0. From our step size, we get x1 is equal to 0.1. We're going to expect 5 steps. y1 is equal to y0, which is 0, plus step size 0.1 times our function evaluated at 0, 0. So what was our function? Well, if we go back, we have that dq dt is equal to 4 times 3 minus q. That's our function. So evaluated at 0, 0, we get that this is simply going to be 12. So this is equal to 1.2. Second step, x2 is equal to 0.1 plus 0.1, which is 0.2. And y2 is equal to y1, which is 1.2 plus our step size times the value of our function at the point 0.1, 1.2. So this is 4 times 3 minus 1.2. This is equal to 1.92. All right, third step, x3 is equal to 0.3, and y3 is equal to y2, which is 1.92, plus our step size, times the value of the function at 0.2, 1.92, which is 4 times 3 minus 1.92, which is equal to 2.352. Our fourth step, x4, is equal to 0.4. And y4 is equal to y3, which I'll just represent as y3 for brevity. Plus our step value times the function evaluated at the point 0.3 y3, which is going to be 4 times 3 minus y3. This is equal to 2.6112. And finally, in step 5, we have x5 is equal to 0.5, and we have as an approximation y of 0.5 is about equal to y5, which is equal to y4 plus 0.1 times 4 times 3 minus y4. And this is equal to 2.76672. So this is our approximation to y of 0.5. Which can also be written more briefly as 2.77 Since this is in charge, we're looking at coulombs.